We're on to Newton's third law, the law of action and reaction. This is Newton's most misunderstood law, so we'll go through it slowly and make sure you're not confused about what this law really means. And it is stated as such: for every action force, there's an equal and opposite reaction force. So it sounds very simple. For every force, equal and opposite force. But that's not so. Let's just use an example. In your notes here, it talks about a lawnmower. It said, push on the lawn, the handle of the lawnmower is making you go forward, and it pushes back against you in the opposite direction with just as much force. This is the pressure you feel of the handle against your hand. Okay, so you push on the handle of the lawnmower, pushes back on you with equal and opposite force. And what is making a lawnmower move? Well, you have to think about the whole system. Your hands are attached to the lawnmower and you're pushing on it, but that's it. It's not your hands or your arms that are making the lawnmower move. It's actually your feet. And your feet on the ground, your feet are pushing backward on the ground, and then as a result, the ground pushes you forward. Just stop and think about that for a second. If you're on your feet right now, then walk and think about the act of walking. Why is walking possible? Some people describe walking as a controlled fall. Why is it possible? What are your feet doing when you walk? And you can feel it. You push back on the earth, and the earth pushes back on you. Because the mass of the earth is significantly bigger than your mass, then you get propelled forward. And then there's some other really good examples to make you understand Newton's third law. So here is down in your notes, number one, an action. The tires of a car push on the road, and the reaction is the road pushes on the tires. So which way are the tires pushing on the road? And the answer is they're pushing backward on the road, and therefore the road pushes the car forward. An even better one is number two, swimming. While swimming, if you're doing the free stroke or the crawl, what are you doing? You are pushing the water back behind you, and as a result, the water pushes you forward. And then there are some other ones here. Action at a distance. A rocket pushes out exhaust, and therefore the rocket moves forward. So, and then it even elaborates on that, saying where the original arguments that flight in space was impossible was that there would be nothing to push against because there's no air in space. This action reaction explains how a rocket can fly in space where there is no air to push against. And the last one, the apple pulls down on the earth, therefore the apple pulls up on the earth. And this is, how can this be true? Well, it is true. If the earth is pulling an apple down, then an equal and opposite reaction must be the apple pulling the earth up. And although you can't feel it, when I drop something, if I drop an apple, I can't feel the earth accelerating towards the apple. In theory, it does happen. So let's do this example right here. An apple has a mass of 2 kilograms. Determine the acceleration of the earth. So first of all, if we can find out how much force the earth exerts on the apple, m times a. So the apple is going to accelerate towards the earth, and it has a mass of 2, and it's going to accelerate, we know, at 9.81 meters per second squared. And so we get 19.62 newtons. So it's 19.62 newtons of force on the apple. Newton's third law says there must be an equal and opposite reaction on the earth. So there are 19.62 newtons of force pulling the earth up towards the apple, right, which is actually true. But we're trying to find the acceleration of the earth. So we'll take our formula here. We will rearrange it for acceleration. And then we will put in our 19.62 newtons. And then we will put in the mass. In this one, we obviously use the mass of the apple. Now we'll put the mass of the earth. And the earth is significantly more massive than the apple. In fact, it's 5.97 times 10 to the kilograms, which you can find on the back of your formula sheet. 19.62 divided by 5.97, negative 24, not negative 24, positive 24, equals 3.29 times 10 to the negative 24 meters per second squared. So as you can see, that is a ridiculously small acceleration. There's no way you could actually experience that acceleration. But that is theoretically what happens if you drop a 2-kilogram apple. As it accelerates towards the Earth is accelerating towards it. The forces on both of them are equal and opposite, but because they have different masses, the accelerations are vastly different. All right, what about example number 2? When a rifle fires a bullet, the force of the rifle exerts on the bullet is exactly the same, but in the opposite direction as the force the bullet exerts on the rifle. So the rifle kicks back. The bullet has a mass of 15 and the rifle a mass of 15 grams for the bullet, 6 kilograms for the rifle. The bullet leaves the 75 centimeter long rifle barrel moving at 70 meters per second, which is not really that fast. So first we want to determine, well, I guess we're determining the acceleration of the bullet, but eventually we want to determine the force of the rifle on the bullet, and we want to determine how much force. So when you fire a rifle, you have to have it right against your shoulder, because when it kicks back, the bullet leaves the rifle going one way, let's say to the right. Therefore, there's an equal and opposite force going to the left. And because the rifle has a significantly greater mass, if you don't have the gun right against your shoulder, it could kick back and could damage your shoulder quite severely. So that's why if you're shooting a rifle, you have to have it right against your shoulder and almost lean into it. So first of all, we're going to determine the acceleration of the bullet. How are we going to do that? Well, we have the initial velocity. This is back to kinematics. The initial velocity, we have the final velocity, 70 meters per second. We have the displacement, 0.75. Therefore, we can find the acceleration using kinematics. Because just remember that if you're for a rifle, the acceleration of the bullet all occurs within the barrel of the rifle. Longer barrel means greater acceleration. Vf squared equals vi squared plus 2ad. D equals, we're not trying to find D, we're trying to find A. A equals Vf squared minus vi squared divided by 2d. Right, so stick those numbers into your calculator. That is going to give you an acceleration of 3.3 times 10 to the 3 meters per second squared. So we're talking about a bullet, they accelerate very, very quickly. Well, the acceleration, I should say, the magnitude of the acceleration is very great. B, determine the force of the rifle on the bullet, and C is to determine the acceleration of the rifle. So if we want the force of the rifle on the bullet, then we're going to have to find out the force of the bullet on the rifle, and the force of the rifle on the bullet is equal and opposite, right? Because what do we have? We have the acceleration of the bullet, not the rifle. If the rifle's accelerating at that rate, then you're done. It's going to not only damage your shoulder, it will go right through it, knock your shoulder off your body. So we have the acceleration of the bullet, and we have the mass of the bullet. So therefore, we can find the force, mass times acceleration. What was it, 15 grams? What was it? 5 grams. It was 15. 0.015 kilograms times 3.3 times 10 to the 3. And that gives you 49 newtons. So the bullet is experiencing a force of 49 newtons, and therefore there's going to be an equal and opposite force, 49 newtons, on the rifle. So therefore, the force on the rifle equals, I guess you could say, negative 49. It's equal and opposites. It doesn't really matter because we're not concerned with direction here. Determine the acceleration of the rifle. F equals ma, a equals F over m. We know that the force is 49, and now we know the mass is 6. And we divide those and we get 8.2 meters per second squared. Okay, which is, that's not a slow, it's not a insignificant acceleration. So you want to have it, against your shoulder so that you don't get smacked hard by it. Okay, example number 3. Example number 3 we'll do quickly. It's not really an important example. We just got a couple of identical 20-kilogram shocker cars doing something. The reason you have the two of them, okay, you have them stuck together, you push them into the store, you're running and accelerating at 1.2. Determine the force the second car exerts on the first. This is just more of a theoretical question than anything. The F equals ma. The only question is, you have the acceleration, it's 1.2. The only question is, what's m? You've got two identical cars, they're both 20 kilograms. Is the m 40 kilograms or is it 20 kilograms? And the answer is, it's 20 kilograms. Because the question says, determine the force the second car exerts on the first car. Well, the second car can only exert a force with its own mass. So it would be very illogical to use 40 kilograms. You just multiply those two together and you get, 24 newtons. Easy peasy. It's more of the theoretical concept of what is causing the force on the first car. It's the mass of the second car. Same thing with this question here. Once you get into the store, you see an employee pushing 2 boxes out of stockroom. The employee is pushing with a force that causes the 2 boxes to accelerate at 1.212. You know that the friction acting on the box of dog whistles is 14.8. Determine the force the dog whistle is applying against the Rice Krispie box. This one's going to require a little more work, but still the same idea. In this one, we have the net force, and this time we have an applied force, and we have a force of friction. And what are we looking for here? We're looking for the applied force. The applied force equals the net force minus the force of friction. And the net force is ma. Force of friction is going to be negative 14.8. Again, I put it negative because I'm going to say that the net force is positive. And the only question I have to ask myself is, what do I use for the mass? Do I use 4.5, 2.36, or do I add them together to get, 7.86? And the answer is, because the question says determine the force the dog whistle box is applying against the Rice Krispie box, I have to use the mass of only the dog whistle box, because the dog whistle box can only apply a force with its own mass. Therefore, the number here is going to be 2.26. It's accelerating at 1.2. Minus really becomes plus. And stick that into your calculator, and you should get 17.4 newtons. All right, and then example 5 says, if I push on the lawnmower, it pushes back on me with equal opposite force. Explain why we don't just stay still. Well, we did that at the beginning of the class, just to summarize it. Is because when you are pushing on the lawnmower with your hands, you're not really pushing on it with your hands. It's your feet. Your feet pushing on the ground. Your lawnmower is just an extension of your arms. So if you have to talk about what forces are acting on what. Your hands are on the lawnmower, but they're not really pushing it. It's your feet pushing on the ground that makes the lawnmower go forward. All right, and that's it for Newton's third law. And do yourself a favor and watch some videos on Newton's third law, action and reaction. because I think it will help solidify the concepts we discussed here. We'll see you for the next lesson.